Space is stretching right now, so why do galaxies still hold? Here is the short answer you can trust today. Local gravity, cooling, and timing beat expansion inside growing clumps. Those clumps become stars, galaxies, and webs across deep time, and the details answer something bigger, like why we exist. Today, we track the race between pulling together and spreading apart. We can watch the whole story from tiny ripples to clusters. By the end, space seems friendly to structure, not empty. Bottom line for now, structures exist because local winds beat global. Stand outside under a dark sky with the Milky Way arching. It looks calm, but everything inside is orbiting fast. A bound system means members stay together despite cosmic expansion. This decides whether atoms, planets, and galaxies can survive time. Cosmic expansion is a speed that scales with distance. Double the separation, double the expansion speed between those points. Inside a galaxy, local gravity pulls harder than that drift. Stars circle the center, exchanging energy and staying gravitationally trapped. The test is simple and very forgiving for small systems. Rule of thumb: internal speeds must outrun Hubble flow locally. Take the Milky Way, about 100,000 light-years wide. Hubble's constant is roughly 70 kilometers per second per megaparsec. Across our disk, that expansion would be only a few kilometers. Meanwhile, stars orbit at about 220 kilometers per second. 220 beats 2, so the galaxy stays together. Zoom smaller and atoms crush expansion completely with electromagnetic binding. An electron's pull toward a proton dwarfs any cosmic stretching. Molecules hold, crystals hold, and your body very much holds. Even the solar system ignores expansion, because gravity wins locally. Planets orbit within a deep potential well carved by the sun. Only at gigantic separations does expansion set the background pace. Galaxies still drift apart overall, riding the stretching cosmic fabric. But inside each halo, the fabric is effectively tied down. Energy gets shuffled and radiated, letting orbits settle and bind. Example in real terms: satellites spiral inward when drag removes energy. So the picture is simple: local binding outruns global stretching. Wind the clock back to a glowing, crowding early universe. Everything was hot, ionized, and almost smooth, with tiny wrinkles. Those wrinkles are density ripples, where some regions are slightly heavier. Heavier regions pull harder, starting the long cascade toward structure. The name for the tipping point is the gene's threshold. It says gravity wins when mass beats pressure over a scale. Pressure fights collapse by moving stuff outward faster than gravity pulls. Cooling reduces pressure, so collapse can proceed and grow clumps. After about 380,000 years, electrons met protons calmly. Neutral atoms formed, light decoupled, and the cosmic microwave background streamed. That cooling lowered pressure, and the gene's scale shrank dramatically. Regions that were safe before now could begin falling inward. Sound waves had been ringing, leaving ripples like faint spherical shells. Those patterns set preferred scales we still trace in galaxies. Tiny test, increase pressure, and collapse slows or even halts. Lower pressure and gravity gets an easier, quicker path inward. The story hinges on timescales, like a race with pit stops. If cooling is slow, pressure hangs on and gravity stalls. If cooling is fast, energy escapes and collapse deepens. Example in real terms: a cloud collapses faster than it can heat. Its heat radiates away through atoms and molecules, mostly hydrogen. Another number helps: the baryon acoustic scale, around 150 megaparsecs. That scale is a fossil ring, visible across galaxy maps today. It is the ghost of early sound, locked into structure. Bottom line here: wrinkles grew as pressure fell, and gravity took over. Now the invisible scaffolding enters, the dark matter we cannot see. Dark matter is matter that barely interacts except through gravity. This stuff does not collide or radiate, so it cools differently. It streams through itself, forming dense knots and long connecting filaments. Those knots are halos, and the filaments are the cosmic highways. Baryons fall onto this lattice, losing energy and settling into centers. So structure first takes shape in the dark, then shines later. Why care about that order? Because timing decides whatever forms. If dark matter were too fast, it would wash out ripples. If it were too warm, small galaxies would never assemble. Cold dark matter stays slow enough so tiny halos can grow. Those halos merge, collide, and swallow, building larger systems over time. Picture a tree of mergers stretching from dwarfs to giant clusters. Gas follows the gravity, shocks at the edges, and heats. Then it radiates that heat and trickles toward the middle. Their disks spin up and stars begin flashing on. Simulations show that web clearly, with filaments feeding hungry galaxies. Example with numbers, a Milky Way halo weighs about 10 to the 12 suns. Dwarf halos can be 1,000,000 times lighter, but still bind. Flows along filaments deliver fresh gas for billions of years. Meanwhile, halos virialize, where random motions balance gravity and equilibrium. That balance makes a stable gravitational container for more assembly. Net result, dark matter provides the skeleton, and baryons paint the flesh. Look closer at the tug-of-war between gravity and pressure. Jean's instability gives the local rule, but the universe adds context. Global expansion stretches coordinates, while perturbations grow by stealing energy from flow. Growth depends on what fills space, matter or radiation or vacuum. During radiation domination, pressure is huge and growth nearly stalls. During matter domination, growth is steady and structures snowball upward. When vacuum energy dominates, growth slows again and structures freeze out. The math compresses to a growth factor that tracks with time. Mechanically, gravity amplifies overdensities, while expansion dilutes them between interactions. The winner depends on relative densities and the expansion history. Example in real terms, the growth function peaks before dark energy rules. After that, new galaxies stop forming in great numbers. Another example, overdense regions collapse by a factor of about 200. That factor sets the contrast between halos and the background medium. You can think of it like a rainfall threshold. If the air is dry, clouds evaporate and rain never forms. If the air saturates, droplets stick and storms can grow. Here, density plays the role of humidity, setting clumping chances. Bottom line, growth runs fastest when matter rules, then slows once vacuum leads. We can actually measure the dials that set this entire balance. Cosmologists track fractions of energy in matter, radiation, and vacuum. They also track the fluctuation strength and the present expansion rate. Together, those numbers forecast how much structure the universe can grow. One fraction is the matter density, often called omega matter. Another is the vacuum fraction, nicknamed omega lambda by tradition. The fluctuation strength today is sigma 8, describing 8 megaparsec clumpiness. And the expansion rate is h0, our local Hubble rate. Rough values today are around 0.3 for matter, around 0.7 for vacuum, and about 0.8 for sigma 8. h0 sits near 70 with an ongoing measurement tension. The picture is simple: more matter means faster growth up to limits. More vacuum energy means earlier freeze-out and fewer late galaxies. Stronger initial ripples give earlier collapse, priming small halos to form. Example in real terms, double sigma 8 and clusters arrive much earlier. But double vacuum and much of that gain evaporates quickly. Another example, if vacuum were 10 times stronger, galaxies barely appear. If it were 10 times smaller, massive clusters would dominate longer. Observations pin us near a narrow window where galaxies flourish. That window is not razor thin, but it is selective. Bottom line, measured parameters explain why structure grows enough, yet not too much. Galaxies are not quiet gardens, they are messy, windy construction sites. Feedback is the pushback from stars and black holes on gas. It matters because unchecked cooling would dump all gas into stars. Then galaxies would quench early, leaving little room for long stories. Supernovae inject momentum, heat, and metals, stirring the interstellar medium. Young stars blast ultraviolet light, carving bubbles and evaporating dense clumps. Black holes launch jets and winds, punching holes through galaxy halos. Those outflows toss gas outward, where it can cool again slowly. The cycle prevents a runaway and sets a self-regulating rhythm. Mechanically, turbulence, shock heating, and radiation pressure throttle star formation rates. Gas leaves, cools, returns, and forms new stars in bursts. The pauses matter, because pauses keep disks from collapsing catastrophically. Example in real terms, M82 drives 1,000 km/second winds. Another case, galaxy clusters show cavities blown by central black hole activity. Those cavities displace hot gas, delaying cooling across vast intracluster regions. The result is fewer stars than naive cooling models once predicted. That sparseness matches observations, lending confidence to the feedback picture. Tiny tests remove feedback in simulations, and galaxies become unrealistically dense. With feedback restored, sizes, colors, and gas fractions look right. So the picture is this: feedback sculpts galaxies, preventing overbuilt structures. Now zoom into a cold, dark molecular cloud 100 light-years wide. The scene is velvet black, with threads of dust and ice. Radiative cooling lets gas shed heat faster than it compresses. That is the trick that unlocks stars, planets, and chemistry. Hydrogen molecules rotate and vibrate, emitting photons that carry energy away. With metals and dust, cooling improves further, and fragmentation speeds up. Fragments spin, flatten, and grow into disks feeding young protostars. Gravity deepens the wells, and disks launch gentle, stabilizing outflows. Those outflows remove angular momentum, allowing more gas to fall inward. Newborn stars ignite fusion, lighting cavities like lanterns in a cave. Around them, disks assemble pebbles into planetesimals and planetary cores. Collisions stick because gas cushions impacts and removes relative speed. The star does not eat everything because heating puffs the disk. Gaps open, migrations shuffle orbits, and resonances carve elegant patterns. After a few million years, a stable architecture often emerges. Example in real terms, the Orion complex births thousands of stars. Typical efficiency is a few percent, leaving most gas as leftovers. That leftover gas fuels later generations, keeping galaxies forming for eons. Rule of thumb, cooling plus rotation plus feedback equals sustainable star formation. So the picture is, cooling turns gravity into stars and stars into neighborhoods. There is a deeper twist hiding in the background geometry of space. 3 dimensions make gravity fall off as 1 over distance squared. That exact fall-off allows stable orbits and stable atomic structures. Change the number of dimensions and that balance collapses quickly. In 4 spatial dimensions, gravity weakens too fast for reliable orbits. In 2 dimensions, paths loop weirdly and binding hardly persists. The same goes for the electromagnetic force binding electrons to nuclei. The strength of that pull is the fine structure constant. It is about 1 over 137 at low energies. If that number were much larger, electrons would cling too tightly. Chemistry would stall, and complex molecules would struggle to form. If it were much smaller, bonds would be fragile and fleeting. Stars also need a delicate balance of forces and constants. Gravity must squeeze hard enough, but not collapse everything instantly. Quantum pressure and nuclear physics set the resistance to that squeeze. Together, they enable long-lived stars that slowly brew heavier elements. Another stabilizing detail, angular momentum protects orbits from plunging inward. Tidal torques between proto-galaxies help set that initial spin. Example in real terms, planetary orbits stay stable for billions of years. The solar system has lasted 4.5 billion years already. Atoms also stay intact, letting DNA persist and function for lifetimes. What to remember, our laws and dimensions permit stability across many scales. We started with a blunt question: why does anything hold together? The journey crossed ripples, scaffolds, cooling, and the breaks called feedback. We also saw numbers that steer growth toward a sweet zone. Put simply, local winds beat global because timing and energy cooperate. Early wrinkles grew as pressure fell, and dark matter guided assembly. Gas cooled, disks formed, and stars rose within balanced halos. Later, vacuum energy slowed growth, freezing the big picture in place. That pause preserved what had already formed, giving galaxies room to mature. The callback to our opening is clear: expansion loses locally. It loses where gravity, cooling, and angular momentum team up. Across that balance, space allows structures to persist for eons. If that fascinated you, share this with one curious friend. Thanks for hanging out under the stars tonight, and take care.